It's
Are you unmute?
I am unmuted. Yeah.
Yeah. Okay. Hey, hello everyone, and welcome to this week's colloquium. Today we have Mikhail De Villiers. He's going to talk about his master's project, which he successfully finished. So we will talk about probing optical and H1 diffuse gas in MHONGOOSE galaxies.
Yeah.
Okay, thank you, and floor is yours.
Okay, thank you so much. So, hi everyone, my name is Mikhail De Villiers. Currently, I'm a PhD student at UCT and also the observatory. But today, I'm going to be speaking about sort of what encapsulates my entire master's thesis, which was titled Probing for Optical and H1 Diffuse Gas in MHONGOOSE Galaxy UGCA 250. And for my master's, I was supervised by Dr. Mokotsi and also Professor DJ Pasano. So, a bit about my research I did for my master's. It's a kinematic study of MHONGOOSE Galaxy UGCA 250, mainly trying to sort of get a feel for and see what the gas dynamics actually is in this galaxy. But more importantly, I was looking for signatures of extraplanar gas. And extraplanar gas, simply put, is gas that sort of exists as part of the galaxy, but it exists a bit further out, part of the halo of the galaxy, and rotates a bit slower. I'll be getting into much more detail about extraplanar gas a bit later on. But I was looking for extraplanar gas in both the optical by using SALT RSS data, as well as the radio by using MeerKAT H1 data. And one of the main takeaways from my thesis was that this illustrates how high-resolution optical spectroscopy can be combined with MeerKAT H1 observations to obtain a comprehensive study of the gas kinematics in a galaxy. And this is also contributing to the larger collaboration of which my galaxy belongs to, which is MHONGOOSE. So MHONGOOSE is a large survey project of MeerKAT, looking at 50 nearby galaxies, which cover a range of inclinations and also H1 mass coverages. And they also have ranging morphologies going from your dwarf galaxies to more grand design spirals. So it's a really comprehensive sample of different types of galaxies. And what makes MHONGOOSE a bit more special is that this data is obtained by utilizing the unprecedented combination of high sensitivity and high spatial resolution that MeerKAT can achieve. And in this way, MHONGOOSE sort of serves as a successor to previous nearby exogalactic surveys such as THINGS or halo gas, which would only be able to attain one of those two qualities in service of the other. So, for example, THINGS would have high spatial resolution, but then low sensitivity. MHONGOOSE has quite a number of chief scientific aims. I list just a few here, but some of MHONGOOSE's aims is to study the relation between gas and star formation in galaxies, and also deepen our understanding of the baryon cycle, which is the picture of how gas flows in and out and around galaxies. And furthermore, we'd also like to understand the distribution of dark and baryonic matter through using MHONGOOSE. But I should stress that in addition to the MHONGOOSE H1 survey, there's also a SALT program to follow up each one of these galaxies with spectroscopic long-slit data, really getting that high resolution for the innermost, densest regions of these galaxies where you find a lot of ionized gas. But what makes MHONGOOSE so special, and what is MHONGOOSE trying to answer? So another thing that has sort of plagued exogalactic astrophysicists is that the observed star formation rate in the local universes pretty much exceeds the amount of neutral atomic hydrogen that these galaxies contain in the gas reservoirs. So for the local universe to maintain this current observed rate of star formation, galaxies must be refueling the gas reservoirs somehow. And one way that a galaxy can gain more mass is that through minor mergers, where we'd have on the right-hand side here, we'd have a dwarf galaxy getting assimilated into a much larger spiral galaxy, increasing the overall atomic gas content. But some studies, such as Di Teodoro and Fraternali, 2014, have shown that minor mergers alone cannot supply the required quantity of gas. So that begs the question that gas must be coming from somewhere, right? Because these galaxies need to have this certain amount of gas to maintain the star formation. So the leading scenario is that some form of gas accretion is occurring in this galaxy. And there are essentially two schools of thought as to how this gas is treated. Either recycled gas is being accreted into the galaxy. For example, the gas leaves the disk of the galaxy and comes back to the galaxy eventually. Or there is some accretion from the cosmic web where galaxies would accrete fresh gas from the intergalactic medium, the space in between galaxies. And this accretion of fresh gas is further subdivided into two different scenarios which have been justified by cosmological simulations. So we'd either have hot accretion, where hot gas would settle onto the galaxy and be shock heated, and eventually, if it reaches a high enough gas densities, it would settle onto the disk of the galaxy. Opposed to this, we'd also have something called cold accretion, which is where, simply put, gas would move through these filamentary structures and in sort of clumps and eventually settle onto the disk of the galaxy. But one problem with this was that cold accretion, the simulation suggests that cold accretion would have these filamentary structures with very low column densities. And this is sort of beyond the observational limit of what our telescopes can achieve, except for MeerKAT, which is sensitive enough to detect these low column densities through MHONGOOSE, so it can further understand how gas moves in and out or just into galaxies. But if gas is moving in and out or just into or out of galaxies, there must be the sort of intermediate stage where the gas is kind of part of the galaxy, but not exactly part of the disk of the galaxy. And this is what we call extraplanar gas, which is what I'm mainly looking for. So extraplanar gas, abbreviated to EPG, observations of nearby spirals have provided evidence for large amounts of atomic hydrogen H1 in these galactic halos. So a noteworthy example is on the right here, which is NGC 891. And as you can see, the moment zero contours of the H1 extend significantly further than what we see from just the optical disk. And extraplanar gas has many properties. For one, it's typically more diffuse than the gas you find in the disk. It also shows a lagging rotation with respect to the gas in the disk, and it has a scale height of several kiloparsecs. And similar to how gas is accreted in and out of galaxies, there are also main classes of mechanisms as to how EPG can actually come to be and coalesce and exist as a galactic halo. So either people believe there's some sort of inflow model where gas is accreted from the intergalactic medium, or we have an outflow model where gas is expelled from the disk of the galaxy via some violent process such as superbubble outbreaks, high star formation rate, or supernova, where the gas gets ejected from the galaxy and then exists in the halo as neutral gas. And just our neutral atomic hydrogen as extraplanar gas can exist as extraplanar gas. We also have its ionized counterpart, which I call eDIG, which is extraplanar diffuse ionized gas. So as its name suggests, this is just extraplanar gas that is ionized. And this is most prevalent in late-type star-forming galaxies, reason being that oftentimes hot, young O and B stellar populations, they tend to ionize their surroundings. And this results in gas getting ejected from the disk via stellar winds and then reside just outside the disk as extraplanar diffuse ionized gas. There are many scenarios as to how this gas can actually get ejected from the disk, and it's usually due to some vehement process such as supernovae, superbubble expansions, galactic fountains, or a high star formation rate in your galaxy. Some ways to distinguish eDIG and see some of these properties is by looking at the flux ratios of nitrogen 2 over H alpha, which are elevated with distance from the disk. And also it must be stressed when I speak about nitrogen 2 in this work, I'm speaking about the nitrogen 2 line that comes off the H alpha, so N26583. And the main reason as to how this is a diagnostic is in the disk of the galaxy, the main source of ionization is your hot O and B young stars. So typically your H alpha would dominate the intensity and the flux when looking at spectra through those regions. However, in the extraplanar layers of diffuse gas, we don't have these young stellar populations. So there must be some other kind of ionization mechanism ionizing that diffuse gas. And tracing the ratio of some forbidden emission lines, I'm using nitrogen 2, but sulfur 2 or O2 can also work. We can actually assess the trend and see whether ionization mechanisms are different with respect to distance from the disk. And that is an indicator of explained diffuse ionized gas. Another way to assess whether we do indeed have eDIG is by looking at the velocity dispersions, which are typically higher than your typical H2 regions, which exist in your disk. And you'd also have a kinematic lag with respect to the disk, similar to how neutral atomic hydrogen will also lag with respect to the gas in its disk. And on the right-hand side here, I have an observational setup taken from UGCA 2019. We use optical long slits to assess the potential eDIG in this galaxy. So if we look at S2, this long slit is placed along the major axis, but just offset, so parallel to the major axis, sort of in a region where eDIG could be expected. And they also place slits S1 and S3 along the minor axis and parallel to the minor axis, so they can sort of assess the distribution of ionized gas as a function of height from the disk. And it must also be said that eDIG has a range of morphologies. It can exist as plumes, as maybe a ubiquitous sea in one region. So they compare different regions of the galaxy just to see what kind of morphologies of eDIG they could potentially detect. So that brings me to my work. So for my galaxy, I was looking at UGCA 250 as pictured on the right here. This is a lake type spiral galaxy, and it's also viewed edge on. It has an inclination about 80 degrees. So I'm pretty much just looking at a thin stripe along the line, along the sky. And it's about 20 megaparsecs away, which is on the tail end of MHONGOOSE's distance sample. It also has a systemic velocity of about 1,700 kilometers per second, and has an H1 mass of 10 solar masses. And if we look at the actual shape of the galaxy, we can see there's apparently a warp in the ionized disk. So this brings me to the actual data that I used for my thesis. So I used both. Yes. Log 10 side. Yeah. Okay. For my data, I was using SALT RSS long slit data. I would use 0.6 arc second by 8 arc minute long slits. And initial observations included the long slits placed along the major axis of the galaxy, as well as the minor axis. And this is overlaid on an R band, on an H alpha band image of my galaxy. I also used the high resolution PG2300 rating, and this gave a wavelength coverage of 5,800 to about 6,700 angstroms. So we're really looking for that H alpha line and looking to model and probe that line. And I did all the reduction with IRAF. So for those unfamiliar with what SALT RSA spectra looks like, for an extended source, that is, we'd have the wavelength axis on the x-axis, and on the y-axis is the spatial axis. And these are the three emission lines I'm looking at. Well, out of those three, I'm actually only looking at two, but we have a very bright H alpha line in the middle, surrounded by two nitrogen 2 lines on either side of it. But I don't want to look at just the gas in the disk, right? So we're looking for eDIG. So potentially this might exist just off the disk of the galaxy. So follow-up observations included placing long slits just above and just below the galaxy in regions where it would be like, oh, if there is eDIG, it will probably be here. And then furthermore, we then place two more slits now parallel to the minor axis in the cyan, offset at 1 arc minute, either towards the approaching side or to the receding side of the galaxy, just to see what the vertical distribution of the ionized gas is in different regions. And then finally, I overplot the MHONGOOSE, the H1 moment zero contours, and we see that the H1 contours do stretch a bit far from the disk, especially the ionized disk. And for my analysis, I was using the MHONGOOSE, or one MHONGOOSE full depth cube. There's a 55-hour observation. It also has a spectral resolution of 1.4 kilometers per second, which some would deem adequate for some kinematic modeling. There's also a beam size 14.37 by 9.82 arc seconds. And this is what the moment 1 and moment 2 maps look like of my galaxy. So a moment 1 map just is a velocity field describing how the velocities are distributed throughout the entire galaxy. So we see we have what we expect is a rotating the H1 disk, and there's also some funny kinematics going just off the disk above and below. And then on the right-hand side is a moment 2 map of the galaxy. This is basically showing the velocity dispersion throughout the galaxy, which is a measure of the spread of velocities around the mean velocity, and it's related to the width of the actual velocity profiles in each of those points. And we see most of this velocity dispersion is fairly normal. It's what we'd expect from the H1 line. Just in the middle, we have a lot of high velocity dispersions, but we kind of expect this because that's where our gas is the most densest. So then we get into sort of the analysis I actually did for my thesis. So for the optical analysis, I was fitting the H alpha and nitrogen 2 emission lines through simple Gaussian function fits. And this would allow me to derive kinematic properties such as the rotation velocities and velocity dispersions of the gas. So I would first be fitting both the H alpha and nitrogen 2 lines with a single Gaussian function as shown on the top. But one thing I noticed is that some of these profiles have broadened wings of emission at the base of the profile. So if you look at the top figure on the right-hand side of the Gaussian function, there's sort of dot points that can't be modeled efficiently by a single function. So then I decided to adopt a two-component fit, where I'd say that these emission lines are constituted by both a narrow and a broader component, a Gaussian component each. And this also has the physical motivation that when you have emission from your standard H2, dense planar H2 regions of ionized gas in a galaxy, they usually produce emission of a narrow component. And then the broad component is typically constituted by a diffuse gas or your extraplane diffuse gas if you find any. And this would also allow me to assess the trend in nitrogen 2 over H alpha by comparing what I get from each of these fits. But since I'm fitting a two-component fit to H alpha and I want to compare ratios with nitrogen 2, I'd also need to conduct a two-component fit on nitrogen 2 as well. So when I'm doing this, I would first have to fit H alpha because it's typically at a high signal to noise. And now knowing each one of these fit components for H alpha, I can then intrinsically tie those velocities to my fit components in nitrogen 2, so that I make sure I'm comparing the same regions of gas. And when I've fitted these for all of my long slits, which are about 6 of them, then I can finally get some results. So yeah, the first results I obtained were rotation curves along the major axis. So on the right-hand side, on the left-hand side, we have in the black dot points is the rotation curve of H alpha through the main disk of the galaxy, through the major axis. And then in the blue, light blue plots is the rotation curve by nitrogen 2, which traces the H alpha. And then the purple and green dot points, they correspond to the rotation curves derived from a long slits placed just above and below the disk. So we're trying to see if there is any real kinematic lag. And we do see, for the most part, that when we compare the velocities just above and below the disk with that in the disk, we do see what appears to be a kinematic lag of about 20 kilometers per second. And this is indeed consistent with lags of eDIG commonly reported, such as by Fraternelli 2004, which show that eDIG typically lags at a few tens of kilometers per second per kiloparsec. So it is consistent with that. But you might be wondering, so why does the purple only be on one side and why does the green only be on one side? So if I go back to my observational setup, you actually see on the white long slits, on the top one only probes emission from this side of the galaxy, and the long slit at the bottom only probes emission on the left-hand side of the galaxy as we are looking at it. And that's sort of a result of how the warp of the galaxy is. So, and then furthermore, also on the right-hand side, I have the rotation curve through the major axis from both the broad and the narrow components, as well as overlaid with the single component rotation velocities. Now, if you were to have sort of a definitive layer of extraplane diffuse ionized gas, you'd see, ideally, you'd want to see broad components consistently lagging behind the narrow components. We don't see that here. We see a lot of variation as to which component actually lags or has a high or slow velocity in certain instances between the orange and blue components or dot points. On the right-hand side, though, we do see blue dot points somewhat steadily lagging behind the narrow components, but this still isn't definitive enough because it still traces some of the single component velocities. So this is mostly stating that a lot of these broad components could be constituted by diffuse ionized gas, which exists within the plane of the disk of the galaxy as opposed to it being extraplanar, since it's not lagging. And then similarly, I also compared the rotation curves of all my minor axis long slit observations. So going through the minor axis and then the two observations parallel to them. And And if we look at the minor axis rotation curve in the black dot points, we see that it mostly traces the systemic velocity of the galaxy. Now, to see clear indications of a lag when looking through minor axis rotation curves, you sort of see a shallowing of the velocities as we extend from at great distances. So if you look at the one arc minute receding curve, which is on the top, on the outer side, it does sort of shallow its velocity and go towards the systemic velocity, and the same can be said about the approaching side. But these velocities are still all contained within a very small scale height and don't exceed that of the minor axis, so it still isn't really indicative of any lagging explained layer. And then similarly, as I did with a major axis curve, I also produced a 2-component minor axis rotation curve with our broad velocities in the blue and our narrow component velocities in the orange. Here we see broad components kind of slightly higher than the narrow and broad components slightly lower than the narrow on the other side of the galaxy. But once again, these aren't consistently lagging components because there is a lot of variation as to which lags. Is it the narrow? Is it the broad in certain places? So this still doesn't give us any strong indicators of a lagging diffuse ionized gas layer. And then similarly, as I decompose the minor axis rotation curve, I did the same for the long slit observations on the approaching side and receiving side of the galaxy, so parallel to the minor axis. And once again, I don't see any clear indications of a consistently lagging broad component. We see instances, but this is still not definitive enough to say whether there is a lagging layer of explained diffuse ionized gas. But that was only one diagnostic, looking at the rotation velocities and trying to determine whether there was a lag. But another way is to investigate the velocity dispersion. So studies have shown that the velocity dispersion in diffuse ionized gas is much higher than that of your typical planar H2 regions. So along the major axis, these are the velocity dispersion values of my single component fits on the left and my 2-component fits on the right. So largely the single component velocity dispersions are consistent with that of H2 regions, which are usually about 20 to 30 kilometers per second throughout the entire disk. But one thing that needs to be stressed is that this galaxy is extremely highly inclined. It's at 80 degrees inclination. So when you're looking through a single line of sight, your line of sight essentially samples emission from many different H2 regions. So that could explain some of the broader profiles because it's not in too much excess to sort of be indicative of an explained diffuse ionized gas layer. And then when we look at the 2-component velocity dispersions on the right-hand side, we see that the narrow components are consistent with the velocity dispersions from H2 regions, all around 20 kilometers per second. And there isn't too much variation in the broad components, except for on the left-hand side of the plot, where that kind of coincides with the massive spike of velocity dispersion we see in the single component fits. But this still isn't really indicative of any explained diffuse ionized gas layer, especially when we compare the fact with that in this region of the rotation velocities, we don't see any vehement lag. So this might just be constituted to diffuse ionized gas in the plane of the disk of the galaxy.
If you look at that, so it looks like correlated noise, right?
Yeah.
They're just below 50 seconds. If you just look at the image, the optical image of your galaxy, what's going on there with that?
This side.
Yeah.
So about 50 seconds would be this side.
So there's
nothing really.
There is like an arm there or something that would make you think there should be that. I mean, there's more than one of those things, right? Yeah,
so exactly that. You could also say this kind of looks sort of systematic, the way it's increasing and decreasing. So you could even think that since it is a spiral galaxy, maybe it's just sort of coinciding with some of the arms at these places, sort of giving that illusion of high dispersion. That could also be another factor, yes. And then furthermore, I also looked at the velocity dispersions of the minor axis. So for my 3 minor axis slits on the left-hand side, we have the velocity dispersions for the minor axis approaching and the receding side of the single components. And for the most part, they are all in good agreement. There's nothing excessive, no sort of data points that are indicative of some sort of activity such as a galactic fountain. These all seem fairly normal, for a lack of a better word. Especially in the middle, we can see that it's sort of tough to separate. So all of these are indicative mostly of just standard H2 regions. And similarly, when we look at the minor axis velocity dispersion 2 components, we also see that narrow components pretty much consistent with H2 regions, and the broad components also fairly well behaved, not really in excess of any great velocity dispersion. But one other important diagnostic is looking also at the flux ratio. So comparing nitrogen 2 over H alpha as a function of distance from the disk of the galaxy. So for this, I would use my minor axis slits. That's where they would be most vital. And if we were to see a sort of clear indicator or the presence of an eDIG layer in this plot, we'd see a steadily rising flux ratio with distance from the galaxy. But we don't see that here, especially in the minor axis or the black dot points. We kind of see a disparity in how the ratios behave on either side of the galaxy. And similarly, in the approaching and the receding side, we kind of see something increases, but there is nothing sort of indicative of an extraplanar layer, because these don't stretch out as far and they still contain within a very small scale height. So we're thinking that's just part of the galaxy, and these ratios are all low. None of them reach unity. And then similarly, I also compare the flux ratios of my two component fits. So I'm comparing the broad component in nitrogen 2, broad component in H alpha, narrow to narrow. And similarly, we'd also expect to see a rise in the ratios if we were to see an eDIG layer. And another way of also looking at the two component fits was if the broad component dominates throughout, that would be more indicative of a diffuse ionized gas layer, but we don't see that here. As you can see, sometimes the narrow component ratios exceed that of broad, and there's no clear indication of increasing excessively on either side. So main thing I got from the optical results was that there's sort of no strong evidence for a layer of eDIG. So that's what I did for my optical analysis. That was one half of my thesis. And for the H1 analysis, the main thing I started with was by performing tilted ring modeling through the means of using 3D Barolo. So a tilted ring model is a way to describe the gas dynamics of a galaxy by modeling the galaxy as a set of concentric rings. So in my research, I'll be modeling this galaxy as a set of concentric rings, each of the same width, but each one of them would have a unique rotation velocity, a unique velocity dispersion, a unique inclination, and a unique position angle. So I'm really trying to model the entire galaxy like this. And I explored sort of 3 different ways to model this galaxy. One would be to model the entire galaxy simultaneously. One would be to model only the approaching side, and one would be to model only the receding side. And all my models were treated as a single disk. So only sort of one set of concentric rings like this. And these are what some of my models look like. So on the left-hand side, I have my model for both sides of the galaxy at once. Middle, I have the approaching side. And on the right, I have the receding side. So, and in each one of the rows, I have moment 0 map first row, moment 1 map second row, and moment 2 map third row. And in the columns, I have datum, model, residual. So the main thing you want to look at for this is how well your moment 1 map shows that your model is actually working. So if you compare the residual plots, we see that the both sides, it does the worst job. So it's pretty much inefficient to model this galaxy as two halves simultaneously because of the asymmetry in it. But then we also see that both the approaching side and the receding side, by looking at the moment 1 residuals, they sort of have strengths and weaknesses as to which side they model better, which is what is expected. But for the main purpose, I would have to be treating both halves independently because of the galaxy's asymmetry. And this is also shown in how the inclination and position angle changes throughout the galaxy. So for the large part, the inclination angle, which is shown in the blue, is largely showing the same trend for each of the models. But we mostly focus on the approaching and receding sides, which do show a bit of difference, and especially the position angle of the approaching side pretty much has a sort of linear trend, while the receding side has what resembles a bit of a sine wave. And the inclination and position angles when fitting these actual models were all regularized by a third order polynomial, just to sort of make sure that no unphysical discontinuities actually arise in our models. Another way to assess your sort of goodness of model is to be by taking position velocity diagrams and assessing how well your model and your data sort of mimic each other. So in each one of these plots, I have the position velocity diagram along the major axis in the top row and then along the minor axis in the bottom row. And this is taken of both the model and the data. So in the blue contours, we have the contours from the data, and the red contours of the data is the model. And to assess how well a model is fitting, you basically want to see how well the red contours mimic that of the blue contours. So if we look immediately at the one on both sides, we can see that the red is underestimating the presence of gas, pretty much just below where your rotation curve actually settles. And then on the approaching side, we see that on the approaching side of the galaxy in the top left corner of the middle plot, we see that the red is performing quite well and is doing a good job, but is sort of unable to model a bit more blue contour sticking out just below that rotation curve. Similarly, for the receding side rotation curve, we see it also models the gas quite well, much better than the both sides model, but in the center of the galaxy, it's sort of overestimating the presence of gas. So each one of these models do some things well, and in some things can't do well. But that sort of speaks more to the inclination of the galaxy, and we are sort of limited in what we can actually model of this galaxy. Another way to derive kinematic information from this galaxy and H1 data, which I did, was to use the envelope tracing method to derive rotation curves. So once again, my galaxy is highly inclined. So one issue with this is when we have a line of sight going through the galaxy, we're actually sampling emission from many galactocentric radii. So if we look at this figure on the right, the leftmost part, a line of sight going through this velocity field has contributions from the major axis and in all from around. But when we would like to create a rotation curve, we just want the data going through the major axis. So what we do is we collapse all the kinematic information of our galaxy into a position velocity diagram, and then we extract the velocity profile within a certain annulus in our position velocity diagram. And this results in a velocity profile on the rightmost plot, which shows the contribution of different radii in the galaxy. But since the major axis is perpendicular to our line of sight, we expect that to have the greatest sort of contribution. We then fit the velocity profile with as many functions as we can, and we extract the velocity corresponding to the major axis, and then we build up our rotation curve like that. And the main purpose of this is to mitigate projection effects, which results from having galaxies so highly inclined. And when I do this, these are the rotation curves I obtain, which is of the receding and the approaching side, mostly in good agreement with each other. The approaching side is rotating a bit faster than the receding side in the outer regions, but this agrees with what we see in our moment one maps and in also our 3D Barolo tilted ring models. And we further confirm this by comparing all of our rotation curves of H1. So this is our tilted ring model using both sides, tilted ring model only approaching, only receding, and then our two rotation curves from our envelope tracing method from earlier. And we see these are all largely in good agreement, especially when looking at the median velocity from where the rotation curves reach its flat section, so after about 100 arc seconds. And we'll see everything's in good agreement. There may be a bit of differences within the most densest regions below 50 arc seconds, below 100 arc seconds actually. And these are the most densest regions of our galaxy, and this is where we're also most susceptible to beam smearing, which could introduce sort of false measurements in our actual recorded velocities. But that wasn't the only thing I did on the H1. On the H1, I also performed Gaussian decomposition, similar to what I did with the optical emission lines. I would also be either assuming one or two components, and when I'm assuming two components in the H1 cubes, I'm stating that there is either a narrow component which comes as a consequence of the thin disk, or we have a broader component which is sort of the consequence of your diffuse emissions stemming from your thick H1 disk. And then I would separate each of these components into two separate cubes, having essentially a broad and a narrow cube. And this is what the fit component distribution looks like throughout the galaxy. So we have a fit type of either one or two components. And on this plot, on this figure, we see that two components are pretty much all throughout the main disk of the galaxy. It's as expected. And on the outer regions, we see that there's only one component. So you might think, oh, this is just a diffuse sort of capsule that's of diffuse H1 gas that is sort of around our galaxy. But this isn't necessarily true, because the SNR is inherently lower in these outer regions of sort of lower intensity. And so these might just be low SNR, and that's why they present themselves as single components. But then I would go on to create moment one maps of my two component fits. So I'd have narrow component on the left and broad component on the right. And so this is sort of a way to, one way I was exploring kind of to isolate the thin and the thick disks of the galaxies. So immediately when you look at the narrow component, we kind of see in the outer regions it's rotating faster than the broad component. So we do see that there is another diffuse component inside the disk of the galaxy. Whether it's extraplanar or not is still a big question because of its high inclination and can't really disentangle it. But in the outer region, on the receiving side, we have much higher velocities, and in the approaching side, we have much lower velocities, which means if it has low velocities, it's still rotating faster. So the broad is still lagging behind the narrow in most regions. And a better way to visualize this is by taking a velocity difference map between my two moment maps. And we can see if you sort of trace a line through the position angle of the galaxy, you can see there's a big blue section and big blue red section towards the tail ends of either side of the galaxy. And this is sort of hinting that in those regions that the narrow component is sort of steadily rotating a bit faster than the broad component. And especially in the middle, you see a lot of bright colors there. That is where our gas is the densest and beam smearing effects are the most apparent. And then eventually, one of the big results of my thesis was to finally combine all my rotation curves of my H alpha and my H1. So in these two plots, I have the receding on the left and the approaching side of the galaxy on the right. So on the left-hand side, I would have the H alpha and H1 in the disk of the galaxy. Then I would also have the H alpha just above the galaxy in sort of that parallel major axis long slit observation. Then I would also have the H1 velocities that correspond to where the long slit observations are. So that way I'm comparing regions of H alpha in the disk and the regions of H alpha to H1 just off of the disk for both sides, and seeing how well they sort of compare. And on the receiving side, we get an H1 lag of about 8 kilometers per second and an optical lag of about 22 kilometers per second. So these lags do not match up. But when we look at the approaching side, we see that we have an H1 lag of about 19.5 kilometers per second and an optical lag of about 23 kilometers per second, which are much closer together. So suggesting that sort of these exist as the same part of the galaxy, but on the other side there it seems to be some difference, possibly suggesting that what's detected in the H1 there isn't necessarily off the disk and just part of it, and similarly with the optical lag. So with this optical lag, one main issue is that because the disk is so warped, these velocities could maybe just be measured from a larger galactocentric radii as opposed to gas just being above and below the disk. So in summary, there is no strong evidence for a layer of eDIG in my work. There's no clear sign of lagging rotation, no clear enhancement of the flux ratios, and the low star formation rate of the galaxy also kind of aids in support of this finding. We also find extensive H1 in the halo. There's a lot of extraplanar H1 gas, but the single disk model is a bit inefficient to model it. So it requires more detailed modeling, maybe looking at the multi-disk model or including some arcs and spiral arms to better mimic the gas content. And there's also strong evidence for multiple components throughout the galaxy in H1, so that could be explored a bit further. And maybe another step would be to actually model the decomposed cubes individually and then compare the kinematics to actually see whether these stem from a thick and a thin disk and to go take that step further. Thank you.
It was great. You did a lot. Any questions? Both on Zoom and in person? Yep, Xavier.
I have two set of questions. Well, so you're equating the broader components of J and narrow components of the region. Don't you think that you're looking at the disk, multiple narrow components would become broader components?
So that's a big caveat in my study. So just for those online, so the question was basically, I'm making the assumption that there is a narrow and a broad component, one of H2 regions, and then a broad component from diffuse gas. But effectively, when you're looking through the galaxy, so highly inclined, your line of sight penetrates emission from many H2 regions. So you could have many sort of narrow components in your emission line, which sort of just assimilate and amalgamate into one broad component. So yes, that is a point in my discussion as well.
Right. So I usually think that that it's very difficult to divide which one is broad and which is narrow. If you look at face-on, then you don't know how far they are.
Yeah.
So I would have imagined the same circle slightly, probably 30 degrees or something, slightly edge on the side.
Yeah. So, okay. So I'll repeat online. So basically this method is optimal for intermediately inclined galaxies. There's a paper in 2019 where they look at a sample of, say, 19 galaxies, and they compare separating the components kinematically, broad and narrow. And sort of in that view, the broad would consistently be lagging. So it's a bit easier to...
Sorry, I have one more. This is slightly more technical. How do you separate out your one component to component? Like based on how do you say this is one component better?
Okay, so I would first go back. So I would first, okay, for those online, the question is, how do you determine your one component and two component fits? Essentially, how do you determine if emission line is truly one component and if it's truly two component? Okay, good question. So for the one component fit, I would first fit it with a single component, right? And then it's simple signal to noise, and I think I use a signal to noise ratio of about 4. So if I use 4 decks, and then I would say, okay, a single component can now fit this line. Now let's see if a broad component can also fit. I mean, a broad and a narrow component. Then I would fit the broad and a narrow component, and I would also have further sort of quality checks on these. So each one of the heights needs to exceed a certain SNR, and also the integrated area under each component needs to be, I think I said something about like 10 or 15% of the total integrated area of the actual emission line. And then I'd be like, okay, I'm not just fitting noise.
And one final question.
It's a question.
You say that your broad component has to be ignored because
No. Yeah.
Just want to add a quick point to Sarah's actually. It's a quick point. And one of the benefits we maybe thought of that this high time was that, oh, you can visually see that this stuff is clearly above the disk that comes with that one side. But I think having to explore multiple conditions.
Yeah.
Okay, yes, sir.
Can you say a bit more about the next step? So these questions kind of lead to within the mongoose sample, are there ones that
So they are ones, but what I want to do next is sort of compare, look at the two extremes. So looking at the most edge on, like I looked at now, and also the most face on, and then sort of compare different methods to firstly detect exoplanar gas, and then also to separate it from the actual disk of the galaxy.
So can you assume if you look at sort of a range of inclination, different galaxies and different inclinations that they're telling you the same thing? Or this galaxy is different, this one has gas and that one doesn't. Can you assume that you're looking at the same thing at different inclinations with different galaxies?
I mean, I think you could probably come up with a sample that you think are fairly similar galaxies, but
Okay, any more? I don't see any, I see there on the chat.
Oh, I don't see it.
He raised his hands. So Sarah, I think you can ask your
even
question.
Oh, Sriram, you can go ahead, ask a question.
Hey, Mikhail, thanks for a nice talk. Congratulations on your masters. Really cool stuff. I just wanted to ask you a small question for some clarification. What is the scale height that you assume when you model it using 3D Barolo?
Oh, okay. So I model a sort of constant vertical scale height throughout the galaxy, and I think I'm assumed a scale height of 1.6 kiloparsecs.
Okay, cool. And when you're doing your envelope fitting, is there a way to sort of accommodate the warp in PA and inclination?
Yeah, so I would also be correcting for inclination each time I extract the velocity profile. But for the warp itself, I can't really correct for the position angle in the envelope tracing.
Okay, cool. Thank you.
Thank you.
Okay, let's thank Mikhail again. Well done. Okay, thank you everyone.
Very nice.